Hi students, last class we discussed about electrochemistry part 7. So in this class, we are going to discuss the part 8 of electrochemistry. So in the last class we discussed about conductance of electrolytic solution. Conductance of electrolytic solution. So before that, based on Nernst equation and related to that relation to Nernst equation and problems on Nernst equation, we explained that. And right now, conductance of electrolytic solution. See here, conductance of electrolytic solution. So conductance of electrolytic solution. So in the electrolytic solution, if you pass the power, that means electricity. So what are the changes will occur? That we are going to discuss now. So in the conductance of electrolytic solution, there are 5 terms are there that we are to discuss now. So one is the resistance. One is resistance. What is resistance? So how it is related and what are the units of resistance that we discuss right now. And second one is conductance. And the third one is specific conductance. And the fourth one is molar conductance. Fourth one is molar conductance. And the fifth one is equivalent conductance. So these are the 5 terms which are very, very important to discuss about conductance of electrolytic solution. So in this conductance of electrolytic solution, so if you log these 5 terms, it's very, very important, and these are useful for objective purpose and also for a competitive purpose, that is NEET and CET classes also. So now if you take the first one among this one, the first one is resistance. So first one is resistance. So if you take the resistance, so all these conductance of electrolytic solution terms depends upon electrolytic cell. So in the last class we discussed what is electrolytic cell. So if you look at here, this is electrolytic cell. Electrolytic cell, 2 electrodes are there like this. 2 electrodes. These two electrodes are taking a data which is a bad transfer of electricity, and these are connected to battery. These are connected to battery like this. So it is a positive, it is connected to positive terminal, and it is connected to negative terminal of the battery. It is connected to negative terminal of the battery. So here, if you take here, and here we are going to take the solution, NaCl solution. So it is NaCl solution, and that must be fused NaCl. Here we are going to take the fused NaCl solution. So now here, this is a beaker. In this beaker, we are taking NaCl solution, and we are dipping to 2 electrodes which are connected to, one is connected to positive terminal, and the second one is connected to negative terminal of the battery. In the last class we explained this one, electrolytic cell. What is electrolytic cell? So if you pass electric current to this battery, to the electrodes, to the solution, there will be a change in solution. So the solution is splits into Na plus and Cl minus. Cl minus is come to opposite terminal of the battery. That is positive here, Cl minus will come here, and Na plus equal to there. There in the anode and cathode, anode oxidation takes place, in the cathode reduction takes place. So by using this electrolytic cell, we are going to discuss this resistance and all these factors which are in conductance of electrolytic solution. So if you take the first one, the resistance. So what is resistance? What is resistance? See, look at here. Resistance means suppose look at here. When the current is in direction, so if any force that will oppose the flow of current, see, look at here. This is a force. So this will oppose the flow of current. Current is flowing from left to right. This is I means current. Current is flowing from left to right, which will oppose means in opposite direction. This is a current direction. In this current direction, opposite to current direction, any force will exist. That force is called as resistance. So here we can say that resistance is nothing but it is a force. It is nothing but the force that will oppose the flow of current. This phenomenon is known as resistance. So here simply we can write as according to definition of you can write as the phenomena which opposes the flow of current, which opposes the flow of current is called as resistance. The phenomena which opposes the flow of current is called as resistance. Simple. What we explained here, what we discussed here, that only we will do. The phenomena which will oppose the flow of current is called as resistance. So here, when you take here, according to this electrolytic cell, how can you write the mathematical expression for resistance? Resistance. This is the definition. And second point, resistance. See, resistance is directly proportional to length between the two electrodes. It is directly proportional to length between the two electrodes. And inversely proportional to area of cross section. See here, it is directly proportional to length between the two electrodes and inversely proportional to area of cross section. That means if length is more, oppose the flow of current. Look at here. If length is more, length between the electrodes are more, then the force which opposes the flow of current will also more. Like that here, if length is more, force between the force which opposes the flow of current also more. That means here, due to that reason only, R is directly proportional to L. If area of cross section is more, force between the force which opposes the flow of current becomes less. Lesser. So only here R proportional to 1 by A. So finally here we can write it as R proportional to L by A. So here we can write as R is equal to some rho into L by A. This is proportionality constant. Rho. So here this term is rho. This term we can call as rho. And this is here resistivity. This term indicates as rho, and this name is resistivity, or we can say as a specific resistance. Or this is called as specific resistance. So here, units of resistance. How can you write the units of resistance? Units of resistance is here we can write as ohm. Ohm is a unit of resistance. So again I am explaining you. Resistance is a term which is very important in the conductance of electrolytic solution. So these five factors, these five terms depends upon this electrolytic cell only. By using that electrolytic cell, we are going to explain these five terms. Resistance. Resistance means the phenomena which opposes the flow of current. Which opposes the flow of current. Which opposes the flow of current. This process or this phenomenon is called as resistance. Is called as resistance. So resistance is directly proportional to L and inversely proportional to A. What is directly? Length means what? What is L? L means here this is L. Length between the two electrodes. Length between the two electrodes. And A, area of cross section. Area of cross section. So if length is more, length between the two electrodes are more, what will happen? The force which opposes the flow of current is also more. The force which opposes the flow of current also more. So only here by using this, see look at here. If length is more, so now the current flowing is also less. The current flowing is lesser. That means some force is there which opposes the flow of current. That is more. So due to that, by seeing the diagram only, here we wrote that R proportional to L by A. R proportional to L by A. So R is equal to. So to remove this proportionality, we are taking that R is equal to rho into L by A. So this we can call it as a rho. This symbol we can call it as rho, but name is resistivity. Name is resistivity. This proportionality constant here we used in the resistance is resistivity. Or it is also called as a specific resistance. It is also called as specific resistance. And units of resistance is ohm. Units of resistance is ohm. So this is the explanation about resistance. This is very easy. Simple we can say as the force which opposes the flow of current is called as resistance. So for notes, take a screenshot. And next, the second one. So second one, conductance. Second one, conductance. Conductance. Second one is conductance. So what is conductance? So how can you define this conductance? What are the units of conductance? And how can this conductance can be mathematically expressed? Mathematically expressed. So look at here, by using that diagram, by using this diagram only all will explain. Two electrodes and here this will be connected to a battery like this. These are taken in a beaker, these positive electrodes and these are negative electrodes. This is anode and this is cathode. So here this solution is a fused NaCl solution. Fused NaCl solution. So conductance. What is conductance? Simply we can say this is the reverse of conductance. Look at here. Conductance is inversely proportional to R. Simply we can say as reverse of resistance is called as conductance. We can say as reverse of resistance is called as conductance. Or conductance is equal to inversely proportional of resistance. But here, according to here, we cannot explain in the definition way like this. because if it is reverse of resistance means must and should we have to explain the resistance factor also. Resistance factor also. So here, so directly one definition is there to this. That definition we can study here. Conductance is nothing but a measure of ability of electric current to flow a material. Measure of ability of electric current to flow a material. That means one material is there. Suppose if one material is there, so one material is there like this. One material is there like this. So what is the capacity of this material to flow the electric current through it? Electric current through it. That is called as conductance. That is called as conductance. See here, the capacity of this material to flow the electric current through it, that we measure. That is called as conductance. That is called as conductance. So here we can write as look at here, the measure of SURE, the measure of ability of electric current to flow through a material is called as conductance. The measure of ability of electric current to flow through a material is called as conductance. Simply we can say as see, one material is there. From that material, from that material, how much electric current will flow, that we are measuring. That is called as conductance. Or inversely proportional of resistance is called as conductance. So this will take in mathematical expression. This will take in as mathematical expression as, look at here, conductance is equal to 1 by R. Conductance is equal to 1 by R. This here we can write as is equal to 1 by R. Is equal to 1 by R. 1 by R. See here, R is equal to 1 by R. 1 by R. 1 by R. Look at here. C is equal to what is R there? In the previously we studied, R is equal to rho into L by A. We know R is equal to rho into L by A. Previous resistance. So here the 1 by rho into L by A. 1 by rho into L by A. 1 by rho into L by A. So C is equal to 1 by rho into A by L. Look at here. So this is resistance already know. A by L. So C is equal to this proportionality constant taken as kappa K into A by L. This is called as conductivity. Or specific conductance. Look at here. So C is equal to K into A by L. Simply here what we take here, instead of 1 by rho we are taking K. This is called as kappa. So now here K is called as kappa. His name is kappa. We can call it as kappa. It will indicate as kappa. And it is K is equal to, so conductivity. In the previously we wrote rho is equal to resistivity. Like that K is equal to conductivity or specific conductance. Or we can write as a specific conductance. Or we can write as a specific conductance. Look at here. K is a kappa. It can be indicated as kappa. K is equal to conductivity or specific conductance. So look at here. So previously we are taking this one in This is rho, and this indicated as rho, and this is called as resistivity or specific resistance. Like that here also we have this proportionality 1 by over taken as k, and this is kappa. K is equal to conductivity or specific conductance So now here, what are the units of this conductance? What are the units of this conductance? Look at here. You take a screenshot for this notes. Next we will proceed after finishing this. After from here, so see here, C is equal to K into A by L. C is equal to K into A by L. Units of conductance. Units of conductance. Look at it. Units of conductance. See, conductance C is equal to 1 by R. Already we wrote that one. So C is equal to. So what are the units of resistance? Ohm. So 1 by ohm. So it can be called as ohm inverse. It can be called as ohm inverse. It can be called as ohm inverse. This conductance was explained by Simon. So its name is Simon, and its scientist name is Simon. So that name is put as a unit. Simon. So that name they mentioned the unit as his name. So like that Simon. So here units of conductance is ohm inverse or Simon. Ohm inverse or Simon. Ohm inverse or Simon. Ohm inverse or Simon. Next one. So two terms are completed, resistance and conductance. Next, specific conductance. Specific conductance. Look at here. Specific conductance. So specific conductance is indicated by kappa K like this. Specific conductance is indicated by kappa K like this. So how can you define the specific conductance, and what are the units of this specific conductance we are going to discuss right now. Specific conductance. How can you define the specific conductance? See, look at here. Specific conductance is nothing but equal to conductance. And also it is directly proportional to length between these two electrodes. And inversely proportional to area of cross section A. So here specific conductance is nothing but it is equal to conductance, and it is directly proportional to length between the two electrodes, and inversely proportional to area of cross section. You can write as specific conductance is equal to specific conductance is equal to conductance in which electrodes are taken in a beaker. Electrodes are taken in a beaker having electrolyte solution. Of length area of cross section A. Area of cross section area of cross section A. Simply we can take it as a, so here specific conductance is equal to conductance of this electrolytic solution. Conductance of electrolytic solution. Simply you can write like this. This is enough. Conductance of electrolytic solution. Conductance of electrolytic solution. Conductance of electrolytic solution of length L, of length between two electrodes is L, and the area of cross section A, and the area of cross section A, and the area of cross section A, and the area of cross section is A. Specific conductance is nothing but it is equal to conductance of electrolytic solution of length L and area of cross section A. So now here specific conductance K is equal to, look at here, specific conductance K is equal to C into L by A. C into L by A. What is C here? C means conductance. C into L by A. C means conductance. So now here K is equal to C. C conductance units ohm inverse into length centimeter by area centimeter square. Centimeter square. Centimeter square. So now here centimeter square and 1 centimeter will cancel. This one will cancel. So now K is equal to ohm inverse centimeter inverse. Ohm inverse centimeter inverse. Or K is equal to ohm inverse means Simon and centimeter inverse. So these are the units of specific conductance. These are the units of specific conductance. Specific conductance is nothing but is equal to conductance of electrolyte solution having length between two electrodes and area of cross section A. See here, in another way, we can define that conductance is equal to specific conductance. How many? So look at here. Conductance is equal to previously we derived. Conductance is equal to K kappa K into K into A by A. Conductance is equal to K into A. K into A. That only reversely wrote here like this. Reversely wrote here. So it is nothing but conductance. Specific conductance is nothing but is equal to conductance of electrolyte solution of length between the two electrodes L and area of cross section A. So this is about specific conductance, and units are ohm inverse, centimeter inverse, or Simon centimeter inverse. Simon centimeters. So take a note for this one. Next, molar conductance. Next, third one is molar conductance. Molar conductance. This is lambda m. Lambda m is indicated by lambda m. Is indicated by lambda m. Molar conductance is indicated by lambda m. Look at here. Molar conductance. Molar conductance. See, look at here. Molar conductance is equal to is defined as is equal to conductance is equal to specific conductance of solution, this solution, specific conductance of solution, and this solution has to take 1 mole of the electrolyte. Molar conductance is defined as is equal to specific conductance of 1 mole of electrolytic solution. 1 mole of electrolytic solution placed between the two electrodes of length L and area of cross section A. So nothing but look at here. Molar conductance so is equal to what? Specific conductance. Molar conductance is equal to specific conductance of 1 mole of electrolyte per 1 mole of electrolyte or 1 mole of electrolyte or 1 mole of electrolyte. 1 mole of electrolyte placed between the two electrodes of length L and area of cross section A. So here we can indicate as into 1000 by 1000 1 mole per liter will take per liter will take. So now here it can be defined as molar conductance is equal to specific conductance of 1 mole of electrolyte. Simply we can say as this solution what we are taking it is per 1 mole. We are taking per 1 mole. For 1 mole of electrolyte placed between two electrodes. Having length L and area A. This is called as molar conductance definition. Molar conductance is equal to specific conductance of 1 mole of electrolyte placed between two electrodes having length L and area of cross section A. So now here, if you take this is the definition and this is the expression. Expression is this one. And take a screenshot for notes. Then we go for units of this molar conductance. Simply what we have taken here from the limit. See, we are taking the specific conductance per 1 mole. That is nothing but molar conductance. Molar conductance is nothing but it is equal to specific conductance per 1 mole. We are taking the electrolyte. That is nothing but molar conductance. So a molar conductance is equal to specific conductance of 1 mole of electrolyte per 1 mole of electrolyte placed between two electrodes. These two electrodes of length L and area of cross section A. So that is definition. If you go to mathematical expression units, see here. So lambda m is equal to K into molarity. So that will take molarity. So lambda m is equal to K. So what are the units of K? liter. Mole per liter. So lambda m is equal to ohm inverse centimeter inverse mole per liter. Liter means what? Centimeter cube will come. Centimeter cube. So if you take in liter into 1000 centimeter cube, so that numericals number we are not taking here because here we are writing units. So now here lambda m is equal to ohm inverse centimeter cube. Centimeter square will come. Centimeter square by mole. So here by mole. Mole is equal to ohm inverse centimeter square into mole inverse. Lambda m is equal to r. It will be written in ohm inverse means Simon. Centimeter square mole inverse. In SI this is CGS. SI units. You can take it as lambda m is equal to Simon meter square mole inverse. Meter square mole inverse. So this is a molar conductance. Units of molar conductance in CGS and SI units. For notes, take a screenshot. Next up, equivalent conductance. Equivalent conductance. So molar conductance that can be indicated as a lambda m, and equivalent conductance that can be indicated as lambda eq. So here, how can you define the equivalent conductance? Look at here. Same like this, the equivalent conductance is equal to specific conductance of a solution. For equivalent electrolytic solution. For one mole of equivalent electrolytic solution. For the equivalent. Equivalence for 1 mole of equivalent solution. Nothing but here. So lambda m is equal to what we wrote? K by molarity. So lambda eq is equal to K by equivalence. Number of equivalences. Equivalences means we can take as normality there. So in the definition we can write as equivalent conductance is equal to specific conductance for one equivalence of electrolytic solution Say electrolytic solution of length L and area Look at here. So if you take this electrolytic solution as in equivalence, that means in normality, and equivalent conductance is equal to specific conductance in per one equivalence of solution, one electrolytic solution, 1 mole of electrolytic, one equivalence of electrolytic solution. That means here in molar conductance you have taken that 1 mole of electrolytic solution. In equivalent conductance we are taking that for one equivalence of electrolytic solution. 1 equivalence of electrolytic solution. This is the definition. And expression is this one. Here we can write it to 1000. Right? So this is equivalence. Equivalence. So now here if you take the units, here, same like this previous, lambda eq is equal to k by equivalence. Equivalence. That is equal to k is equal to ohm inverse centimeter inverse. So normality by liters. Equivalence means normality by liters. So lambda eq is equal to ohm inverse centimeter inverse normality into cm cube liters. Already previously wrote as cm cube. So that is equal to ohm inverse cm square into normality inverse. So this is the units of equivalent conductance. So here we can write as lambda eq is equal to ohm inverse sin centimeter square and normality whole power 1. So in the SI means sin meter square normality whole power n in the SI means. This is CGS and this SI. So these are the 5 terms we have discussed right now about regarding to conductance of electrolytic solution. Based on these problems we will do the next